Welcome to lecture number 27 of my series on advanced mathematical physics, where over the last few lectures we have been looking at differential forms. Let me give you a quick recap of this. A K-form or a differential form of rank K is a completely antisymmetric smooth 0K tensor. This is how you define a K-form. This means that the K-form omega, when given K smooth vector fields x1, x2 up to xk, returns a smooth function. And this smooth function is obtained in an R multilinear and C infinity multilinear way. What that means is that if any one of the arguments provided to omega, any one of these vector fields, is replaced by a linear combination involving either real numbers or smooth functions, the resulting function that you will get will also be the corresponding linear combination. Now, what we have said so far only goes to show that omega is a 0K tensor. To become a differential form of rank K, the other important demand is that it has to be completely antisymmetric in its arguments, and this property is also called the alternating property. Omega has to be alternating in the sense that if you were to interchange any two of the K arguments that are given to it, say xi and xj here, you are going to end up with an overall minus sign. And this works no matter which pair of arguments you interchange. Now, in the last few lectures, we have actually seen a very important operation that you can do on a differential form. This is the exterior derivative operation, and the corresponding operator d maps a K-form omega into a K plus 1 form called d omega. And the way in which you define d omega is through this particular rather formidable looking expression which involves two sums. Here what we have done is that we have actually defined d omega through its action on K plus 1 smooth vector fields x1, x2 up to xk plus 1, and the right hand side defines the function using omega and the xi's. Note that the original omega, being a K form, can only take K smooth vector fields as the arguments. So in the first sum, the one in blue here, what we have done is to drop one of the K plus 1 arguments and supply the rest to omega. The function you obtain in this manner is acted upon by xi, the particular vector field that had been dropped, and then all this is summed together with a alternating plus minus sign. The second sum involves choosing two distinct vector fields out of this whole set of arguments, dropping them from the list but replacing them by the Lie bracket so that the total number of arguments given to omega is back to K. This yields one function for each pair of I and j chosen, and you weight them again with plus or minus signs and sum up all of them to obtain the second term in the definition for d omega. In the last couple of lectures, we have actually taken a look at many of the consequences of this definition. We have in particular seen that the exterior derivative formula becomes much simpler when you express it in terms of coordinates. Also, we have derived certain properties, the fact that it obeys a Leibniz-like formula, a graded Leibniz formula, when you deal with a product of two forms and do an exterior derivative on them. We have also seen that d applied twice on any differential form yields 0, a singularly important result, which we will have a lot more to talk about later. However, one question might have bothered some of you. Exactly how does one arrive at such a definition? The definition of d omega here is definitely much more complicated and much less natural looking than many of the definitions that we had talked about throughout this course. So, today what we will do is we will really do something a bit unusual in the context of the series of lectures that we have been giving so far. Rather than talk about standard results about differential geometry, I will try to convince you how one could start off with the basic notion of differential forms and think of the exterior derivative as something which will be a kind of derivative and will yield a k+1 form, and try to derive the form for this expression, or rather see exactly why d omega has to be defined in this particular manner. Now let me make a confession upfront. I have not seen the discussion that I am going to share with you in any textbook so far. As a result, there is always a chance that there may be an easier way to see why the form for d omega has to be like this. And if any of you know a better way of figuring out why the formula is like this, please let me know. I would love to be able to discuss that. However, what I will describe to you today is my take on how one could start out from the basic notions of differential forms and end up with this particular definition for the exterior derivative. As I said before, I have not seen this in any textbook, but then again, I have not really seen many textbooks, so there might be a possibility that what I am going to describe to you may already be part of some textbook somewhere. Again, if it is, and you have found a reference where this is described, please do let me know. So here, without further ado, is constructing d omega. So the first thing that we of course demand is if omega is a k form, we want d to act on it to produce a k+1 form. d omega, being a k+1 form, must be able to take k+1 smooth vector fields and produce a smooth function. And this map, d omega, which takes k+1 copies of the set of all smooth vector fields into the set of smooth functions, must have the following properties. It must be alternating. If you were to interchange any two of the vector field arguments, let's say xq and xp here, you are going to end up with a minus sign. It has to be R linear. If you replace any one of the vector fields, let's say the ith one, by a linear combination involving real numbers, you must have, as a result, a linear combination of the corresponding functions, where the individual xi's and yi's were acted upon by d omega, and finally, linearly combined by the same factors a and b. It also has to be C infinity linear, that is, if you were to multiply any one of the argument vector fields by a smooth function, that smooth function can be pulled out of the resulting d omega acting on the whole thing. We will now describe a series of attempts at constructing such d omega, or rather, constructing the action of d omega on the set of k+1 smooth vector fields, and many of these attempts will of course fail, but the failure should show us the way ahead. Now, one thing I definitely ask you to do before you listen to the rest of the lectures, try, if you can, to forget all about the definition of d omega that we have been talking about over the last 3 or 4 lectures, because we are trying to go about this in a way without any preconditions or any biases. Now, our first attempt would be simply something where we have to have a set of k+1 arguments given to d omega, but since omega can only take k arguments, we will just drop one of them. But since there is no reason to drop any particular one of them, we will sum up the resulting functions when you drop each and every one in turn with certain coefficients and then add up the whole thing. Now, the one major problem which this attempt suffers from is the following. If you focus on, say, x1, suppose I were to multiply x1 by a number a, then in all the terms other than the first here, x1 will be one of the arguments in omega, and that function, the resulting function, will be multiplied by the real number a, and all those terms in the sum will have the same common factor a. But the very first term, the one in which I equals 1, is one in which this factor gets dropped. So there, a does not show up at all. Since you are adding up the result of all of these actions in which one term doesn't have a factor of a and the rest has, you are not going to get an overall factor of a. So this is not R linear. So this simple attempt is bound to fail because R linearity is something which is missing here. And it's missing simply because once you drop the xi, that is completely gone. So whatever coefficient multiplied that xi will not show up at all. Now there is a way to correct that, which is simply drop xi from the list. Of course, that is what the hat here signifies. But once you get the function omega acting on x1, x2, xi minus 1, xi plus 1, all the way up to xk plus 1, act upon the resulting function by xi. Then sum up all the resulting functions which come from different values of I going from 1 to k plus 1 with some set of p factors c1, c2, c3 and so on. Now this will be R linear because, for example, if we were to replace x1 by ax1, then as before, all the terms in the sum from I equals 2 to k plus 1 will have ax1 as an argument and will have a pulled out from all the terms. And the very first term, the one which was actually causing us problems before, also has a factor of a coming from the x1 which is now sitting and acting on omega x2, x3 up to xk plus 1. So this is R linear, but is it alternating? Or rather, the question should be, can we choose the coefficient ci to make it alternating? We will see that indeed can be done. So, let's try this. Let's interchange xp and xq, where for the sake of definiteness I have chosen p to be less than q. So p is a smaller number, xp is sitting in the original set of arguments before xq. Now, if we were to interchange xp and xq, then if you focus on this sum, in all of the k plus 1 terms on the RHS, the ones where I is neither equal to p or equal to q are ones in which xp and xq are arguments to omega and they have been interchanged, giving rise to a minus sign. Remember, the original omega is an alternating operator. So, all of those terms automatically change sign. The ones which do not automatically change sign are the ones where I is p or q. So let's compare what these two terms, I equals p or I equals q, were before the interchange and what they become after the interchange. Of course, before the interchange, you had cp times xp acting on omega, x1 through xp minus 1, xp plus 1 with xp dropped from the pth position. So xp plus 1 really is in the pth position here. And then all the way up to xq. Here xq is in the argument list, xp isn't, xp is sitting outside. Note that strictly speaking, this really is not in the qth slot here as an argument for omega. This was in the qth slot in the entire argument list that d omega had. In omega, on the other hand, because xp has gone missing before this position, this really is in the q minus 1th position. As far as the second term is concerned, there the xq goes missing, and it really goes missing from the qx position, because all the vector fields that were in d omega's argument list before that are still here. xp is very much in the px slot, and the missing xq is outside, acting on the whole function obtained by the action of omega on these vector fields. After you interchange the vector fields xp and xq, these two terms take the following form. Remember, it is the vector fields which are being interchanged, not the coefficients, so the cp and cq are still exactly where they were. The xp here is replaced by xq, and of course now xq goes missing, but xq goes missing from the pth position, and xp is sitting here in what is actually the q minus 1s position. On the other hand, in the xp-xq interchanged version of the second term, you get this, where xq is sitting in the actual pth position, and xp would have sat here, but it's missing. Rather, it's sitting outside. Now, if you compare these two pairs with each other, it's obvious that you can compare this term with this one. In both of these, xq is the one which is sitting outside. Similarly, you should be able to compare these two. But the major difference between this and this is in the position of the xp. In the original version, xp really is in the pth slot, and in the interchange version, xp is going and sitting here, which really is a q minus 1s slot. But what is important is between this and this, there are a bunch of vector fields. This is actually xp plus 1 sitting here. Then you have xp plus 2 all the way up to xq minus 1. So these are the dots, the vector fields sitting in between this position and this. So in order to compare the two, what you would need to do is bring xp out here so that it sits in the pth slot. But in order to do that, you have to jump across this many vector fields. And the number of vector fields here, as elementary counting will tell you, is q minus 1 minus p plus 1 plus 1, or q minus p minus 1. So bringing xp forward all the way to ensure that it sits in the same position as it does here will introduce a factor of minus 1 to the q minus p minus 1. And an exactly identical factor will come about if we were to try to move the xq here back to this position, because it will have to jump across exactly the same number of vector fields. So the interchange version becomes this. Now if you want this pair to have a negative sign compared to the original, then what you need is that this factor here must be minus cq. And this factor here, cq times minus 1 to the q minus p minus 1, is minus cp. And for this, what you need is simply this. cp times minus 1 to the power q minus p minus 1 must be, as I said, minus cq. If this works, the other demand automatically falls into place. Now, it's easy to see that this can be rewritten in the form cp by minus 1 to the p is equal to cq by minus 1 to the q. The minus sign gets cancelled with this minus 1 here. So, these are all both equal, and you can call them equal c. And note that this has to hold for any p or q you choose. So, for any I running from 1 to k plus 1, you must have ci equals minus 1 to the I times c. So our attempted d omega, this is really not necessarily d omega yet. We already know it's not, because we definitely gave you the definition of d omega at the very beginning of this lecture. And we have been discussing that over the previous lectures. But at least this particular attempt, d omega acting on x1 through xk plus 1 is c times this sum where I runs from 1 to k plus 1. This is just I. If both are linear, and alternating. But it still has to pass one more test. Is this C infinity M linear? That is, if I were to replace any one of the arguments by a function times that argument, will I be able to pull that function out of this or not? Of course, now that we have actually shown that our sum is alternating, we don't really need to prove full multilinearity. Linearity, that is C infinity M linearity in any one of the arguments will do. So we will try to, just for definiteness, see whether C infinity M linearity works for the first argument. So we start with a function f, which is a smooth function, and look at d omega acting on this. Note that we are calling this d omega, but this really is our attempted d omega, not necessarily the actual d omega. Now, here the sum that we had defined d omega to be, at least our attempted d omega, would break into two pieces. The first one will simply have I equal to 1, the one term where x1 or rather fx1 is outside, omega is getting to act on x2 all the way up to xk plus 1, and the other sum where xi is pulled out and is missing from the argument list of omega, and this I is more than 1 to 2k plus 1, and fx1 was very much an argument to the omega, because omega is C infinity M linear, being a k form. I can actually pull the f out from that. So I have f times omega acting on x1, x2, xi minus 1, xi plus 1 all the way up to xk plus 1. And now we need to make use of the derivative property of a vector field. So the first term that we have here is f times x1 omega x2 up to xk plus 1, which is of course f times whatever we had in the original version without the f. And here xi acting on this product of f times this function breaks in two pieces. In one, it's f times xi acting on the function, and the other in which xi gets to act on f and the function stays intact. But if you take this term and this term together, you actually get f times the original sum. So as far as our attempted d omega is concerned, d omega acting on fx1 with all the other arguments staying the same is f times d omega with the original arguments plus this one additional piece. So our attempt is not C infinity M linear. So we now have to make another attempt. And in this new attempt, we again look for k arguments, that is k out of the k plus 1 vector field which d omega has, to give to omega. And what we do is, instead of dropping one of the arguments, we remove two of them, but replace them by a single vector field. And the most obvious vector field that we can replace a pair of vector fields by is the Lie bracket. So what we do is define another attempt at d omega by this. You take omega, Lie bracket of xi xj with xi and xj missing from this entire set, all the other arguments staying the same, that is saying whatever they were for d omega, and these are weighted by some factors which of course will depend on both I and j and have to sum up over both I and j. And since we want to avoid double counting, we are keeping I less than j. Now here, our attempt, that is attempt number 3, is obviously R linear. Each and every xi is there in some term or the other of the sum, and when you replace xi by a linear combination, that term will give rise to the corresponding linear combination. Adding them all together will actually give you an R linear result. Now, as with our previous attempt, our next question should be, can we choose these coefficients Cij in such a manner that the overall expression becomes alternating? That is, interchanging any two of the arguments here should give you a minus sign. Now, this is what we really want. If we were to take p and q to be any two distinct integers within 1 to k plus 1, and for definiteness we have taken P to be less than Q. In the original set of arguments, we have XP in the pth position and XQ in the qth slot among this argument list for d omega. If you interchange these two vector fields, that is, you had XQ in the pth slot and XP in the qth, you should end up with a minus sign. Now, will that work for our attempted d omega, that is, for this sum? Now, it's easy to see that if the two things which are being interchanged, XP and XQ, are not sitting inside this Lie bracket, but are other terms here, the corresponding term will definitely change sign. That simply follows from the alternating nature of omega. Again, if I and j were P and Q respectively, then you would have the Lie bracket XP, XQ sitting in the first position of omega. And now, interchanging XP and XQ, by virtue of the Lie bracket being anti-commuting, as far as the product is concerned, you would end up with a minus sign for that term as well. So these terms will not give us any trouble. They will actually automatically give us a minus sign no matter what Cij's we choose. The terms which will be more difficult to handle, and also the terms which will actually tell us what specific Cij's can be chosen, are the terms in which one of XP or XQ, but not both, sit inside the Lie bracket. Now, that means that either one of the two indices, I or j, has to be P or Q, and the other index, we could have kept on calling that I or j, but since these are dummy indices anyway, I have decided to call the other index I throughout. Now, we actually end up with a rather complicated set of terms here. Well, not really complicated, but it is difficult to enumerate all of them if you don't think about this clearly. Now, let's begin with the terms which have XP in the Lie bracket. The most obvious one of them will be where you have I is less than P and XI, XP is sitting in the Lie bracket. XI is missing. Of course, I being less than P, this XI missing slot is actually to the left of XP, and XP is also missing. Please note that the slot labeling that we have done here, I, P and Q, are actually with respect to the original set of arguments for d omega. Because of the way in which these arguments have been given to omega, the labels are actually slightly changed. For example, because of the presence of the XI, XP Lie bracket at the very beginning, X1 is not sitting in the first position, it's actually sitting in the second position. And that is going to happen all the way right up to Xi. In any case, we don't really have to bother too much about these issues, because what will really matter for us are the relative positions of these slots, as you will soon see. And because the relative positions are important, we have decided to break up the terms where XP is sitting inside the Lie bracket into three pieces. One of them is precisely this one. The next one is when XP is in the Lie bracket, but the other vector field which is sharing the Lie bracket with it actually has an index which is larger than P, which really means that in our original version, P was I and this was J. But once again, because this is dummy index, I can call it I. That will not change anything. The only important point here is this I does not go from P plus 1 all the way up to K plus 1. This I in this sum, in the second part, is actually less than Q. That means the missing slot here is somewhere in between the slots for xp and xq. And the final piece of the sum, where xp is in the Lie bracket, is again one in which xi is more than p, but here I is actually more than q as well. So the missing slot here is to the right of q. This should not really come as a surprise to those of you who have seen my earlier video where we showed from the coordinate independent definition of the exterior derivative that it really is a k plus 1 form. There also we broke up our sums into these pieces because the relative positions of xi, xp and xq are actually going to be important for the rest of the argument. Of course, these three sums are those where xp is in the Lie bracket and missing from the rest of the argument list. We will also have similar three terms where xq is going to be in the Lie bracket, and now I will have three pieces depending on the relative position of I, p and q. Here I is less than p, of course that means it's less than q as well, and the Lie bracket is xi, xq, and here xi is missing from this earlier ith slot, and that's to the left of xp, and of course that's to the left of the qs slot where xu used to be but is missing from there. Then you have the second sum of this kind where I lies between p and q. So since I is less than q, the bracket is xi, xq, but here the missing slot is to the right of p and to the left of q. And finally you have this third piece where I is more than q, and there the Lie bracket is xq, xi. Remember, the Lie bracket is always xi, xj, where I is less than j. So here, q being the smaller of the two, you have xq, xi, and the xi, the missing slot, is to the right of the qs slot. Now with this in place, we need to talk about what happens when we replace the vector fields xp and xq by each other. That is, interchange them. Now interchanging xp and xq has to be done for all six terms, but let us take a look at these one by one. What happens when I interchange xp and xq in this term? Then what you get is the following. This was the original term. Here, the coefficients and all the other vector fields stay the same. xp is replaced by xq here. Of course, the slot from which xp went missing now has xq missing from the same spot, and you have xp sitting here where xq sat in your original term. Now, if you look at this term where you have xi, xq in the Lie bracket, you would want to compare this in the original essentially with this, where I is less than p, that checks out, and the Lie bracket is xi, xq. Now, there, of course, in the original, you had ciq here, and you also had, and this is more important, xp sitting here and xq missing from here. In our interchanged version, we have xq missing from the ps slot and xp sitting here. So in order to actually make this look exactly like that term, we have to bring xp here. But note that between this missing xq slot, or the ps slot from which xq has gone missing, and this qs slot where xp is sitting now, of course after the interchange, what you have are the following vector fields. You have xp plus 1 sitting right next to xp, then you had xp plus 2 and so on, and just before this you had xq minus 1. So the important question here is, how many vector fields are these? Just a simple count, and the answer is q minus 1 minus p. Now, in order to bring the xp all the way up here, you will have to interchange xp with each and every one of these vector fields. Q minus 1 minus p interchanges, so this brings up a factor of minus 1 to the q minus p minus 1. Now, this has to be the negative of the term which had xi comma xq in the original prior to interchange sums, and this is what you must have. This minus sign, of course, is because you want the xp xq interchange to lead to an overall minus sign. So for this term to give you the negative of this thing, that is minus this thing, you must have the following. CIP times minus 1 to the q minus p minus 1 has to be equal to minus CIQ. Now this can be very easily rewritten in the form CIQ by minus 1 to the q equals CIP by minus 1 to the p, and since this will work no matter which p and q you use, at least for a given I, you must have the following. This pair must be equal to Ci, where we have left open the possibility that the C's for different I's are independent. So at least we end up with this thing. Cij has this dependence on the second index. Cij must be Ci into minus 1 to the j. As long as j is more than I and is sitting to the right of I in the pair, you must have all of them for a given I to take this form, Ci into minus 1 to the j. Of course, this doesn't tell you exactly what Cij's are because we have not determined Ci's, these constants, at the time being. But we will soon. So we have dealt with one of the terms which had I less than p. But in our original sum, we had another one where I is less than p, namely this term. What happens here when you interchange xp and xq? Let's check that out. This was the original term, and after you interchange xp and xq, this is what happens to it. The xq gets replaced by xp, and here of course this xp gets replaced by xq, and the missing slot had xq before, or rather xq went missing from this slot before, and now xp is going missing from this slot, the qth one in the original list. So once again, I can make it look like the terms in the original series by moving the xq back here to its rightful position, so to speak. And for that, again, you have to go across q minus p minus 1 vector field sitting in between, and this is the factor you would accrue. And since we already have the result, the relationship between CIP and CIQ, this actually tells us that CIQ multiplied by this factor will be minus CIP. And this tells us that after you interchange xp and xq, this term here will actually become the negative of this term. No extra information comes out from this because once you have ensured that interchanging xp and xq in the first term will lead to a negative of the fourth sum here, that automatically ensures that interchanging xp and xq in the term number 4 will lead to a negative of the term number 1. So no further constraint on the Cij follows from this. That's some way towards showing that when you interchange xp and xq, in the sum of all these 6 terms, each of which of course is a sum by itself, you get a negative of the overall sum. But we still, as we said, have some more way to go till we get there. Let us now focus on the kind of term where we have the following. I is more than q. So this was the term in the original. After interchange, it simply becomes this. And because this is a term where I is more than q and has x cubed, xi in the Lie bracket, it should be compared in our original sum with this term where I is more than q and you have xq, xi in the Lie bracket. So let's see. How the two shape up. Once again, in the original slot, the major change that has happened is that the P and Q, P here after the interchange is sitting in the Qth slot, but in the original term it was actually sitting in the Pth slot. And you must have got the gist by now. You have to interchange Q minus P minus 1 vector fields to get from here to here. So you get the next from minus 1 to the Q minus P minus 1. So now, in order that this be negative of the sixth sum in our series of sums, you must have the following. Cpi into minus 1 to the Q minus P minus 1 is minus Cqi. Now this looks very much like the condition that we talked about before. But note that there, what you had was Cip and Ciq were being related to each other. Where the first index was the same, the second index could change. Here the first index is the one which is changing. The second index is fixed. And so, we already have the knowledge. And since we already know that Cij depends on the second index in the following manner. Cij is Ci into minus 1 to the j. And we can plug that down here. And what we get is Cpi is Cp into minus 1 to the I. You have to multiply that by minus 1 to the Q minus P. I've just cancelled out the two minus 1s on the two sides of the equation. And Cqi is Cq into minus 1 to the I. Cancelling out the minus 1 to the I gives us a relationship between Cp and Cq. One which should look very familiar to us. It just tells us that Cp over minus 1 to the P is Cq over minus 1 to the Q. And we are now going to call them both C. And note that this ratio is C no matter what values of P and Q you use. So we get Ci is C into minus 1 to the I. Finally, after plugging back this expression, we get Cij is Ci into minus 1 to the j, whereas Ci is C into minus 1 to the I. So the overall thing is C into minus 1 to the I plus j. Now, we had in our original sum, before the interchange that is, another term where I was more than q. If you interchange xp and xq there and make use of this condition for Cij, you will see that once again that will give rise to negative of this particular term that we are dealing with here. So, 4 of these terms change sign into each other when you do the interchange. Notice that by now we have essentially exhausted all the freedom we had for choosing the Cijs. Apart from an overall constant, we don't have any further freedom. Now this means that the other two terms, the one in which I were between P and Q, had better interchange into each other with a negative sign under an interchange of xp and xq with just this condition on Cij. Now if interchanging xp and xq in these two sums where I is between P and Q did not lead to the negative of the other one, then we are out of luck. Then we would have to abandon this particular approach completely. But let us just see what happens. This was a term that you had in the original sum Of course, here CPI we already know is given by C into minus 1 to the P plus I. Now, if you interchange XP and XQ here, this is what you are going to get. XP replaced by XQ, and of course, this XQ replaced by XP. But in order to make it look like the original sum, or rather the other term in the original sum, what you need to do is move this XP all the way out here. But now you have to be a bit more careful. The number of vector fields in between this position and this is no longer Q minus P minus 1 as was the case before. It's actually Q minus P minus 2, simply because the I is sitting in between P and Q, and that's also missing. So in order to go from here to here, where XP has moved all the way to its original spot, you end up with an extra factor of minus 1 to the Q minus P minus 2. As I've written here, 1 less X to jump over. So 1 less minus sign. Now this, if you put them all together, what you get is I plus Q, the P's cancel, and a minus 2 here. That would give you a plus sign. But notice that we have already taken care of another thing at this stage. You had XQ, XI after the interchange. But since Q is more than I, our original sum had XI, XQ. So you have an extra minus sign. So this minus 1 to the minus 2 gives you a plus 1. But this minus sign gives you a minus 1. So with Cij given by C into minus 1 to the I plus j, our term in which I is less than Q but more than P, and XP is in the Lie bracket, ends up giving us the negative of the term where XQ is in the Lie bracket but I is in that same range. And it's rather obvious that if we were to do this to the other term, the one in which XQ is where in the Lie bracket and I was between P and Q, you would get the negative of the term that we are working with here. So ultimately, with Cij given by C into minus 1 to the I plus j, the entire proposed exterior derivative formula does become completely alternating. So our attempt here, where d omega x1 through xk plus 1 takes this particular form. Of course, I have replaced Cij by the form of Cij I need for the alternating thing, is actually both are linear and alternating. So it does pass 2 of the tests for this to be a k plus 1 form. But what about the third and final test? Is it a C infinity M linear object? So to see this, once again, we only have to check C infinity linearity in the first factor. So if we replace the x1 by fx1, we can figure out what will happen. Of course, here you have 2 different kinds of pieces. One in which I is 1. So j can go all the way from 2 to k plus 1. And fx1 is sitting inside the Lie bracket here. The other in which I goes from 2 to k and j goes from I plus 1 to k plus 1. Where I being more than 1, the Lie bracket has some xi, xj, but the factor f is sitting along with x1 in the second position here. Now, this is of course linear in f, the f can be pulled out. But here we have a bit of a problem. The Lie bracket of fxi, fx1 and xj is not f times x1, xj. It actually has one more piece. In addition to f times x1, xj, you have minus xj acting on f times x1. So this actually becomes f times your original proposal plus an additional piece. This is the additional term. So these two together gives you f times the original thing. And this gives you an extra piece which ruins C infinity multilinearity. So this attempt 2 fails. This one fails the C infinity linearity test. So we haven't really progressed much. We have made 3 attempts so far, each one of which had failed on one count or the other. But now let's take stock of where we are. We actually have 2 surviving attempts which pass both R linearity and alternatingness. The first one of them is this one. And note the coefficient C1 here and the C2 and the coefficient C2 here could very well be different constants. So we are calling them C1 and C2. And this is the second attempt which also has passed R linearity and alternatingness, but has failed on the C infinity multilinearity. But let's look at what happens when you change the first factor or first argument of omega to fx1 for both of them. For our first attempt, which we are now calling d1 omega, we do get f times d1 omega, x1, x2 up to xk plus 1, but we have added additional piece. For the second attempt, we again get f times d2 omega with acting on x1 through xk plus 1, but with another additional piece. Now notice that these two additional pieces are exactly identical apart from the factors in front and also the sign, which tells us that if we chose C1 and C2 to be equal, and just added d1 omega with d2 omega, then this piece which was ruining our C infinity multilinearity would actually cancel out. So if you choose C1 equals C2 equals some C, then we are going to get a C infinity multilinear form for d omega. So now this tells us that our definition for d omega, which survives all our 3 tests, R linearity, alternatingness and C infinity linearity, can be defined in this manner. You just take our 2 final attempts and add them together with the same weighting coefficient in front. So what we have now is an expression for d omega which satisfies all our properties except for the fact that we are yet to figure out exactly what this constant C is. Apart from that one niggling thing, everything else has been done. In order to pin down the constant C, what we need to do is take a look at the simplest situation, where omega is a product of a function and a k-form. Remember that if f is just a function, then the exterior product of f with omega is nothing but f times omega. And since d is a kind of derivative, after all we have been calling it an exterior derivative, we would like it to obey a Leibniz relation. We are calling this Leibniz-like because in the general situation, as we have seen earlier already, our definition cannot really be exactly Leibniz. But at least for a function and a k-form, this is exactly Leibniz. D of f wedge omega, we want it to be df wedge omega plus f wedge d omega. But now, if you start with our definition and plug in f omega in place of omega, what you get is simply this. You have this term, our first sum in the definition for d omega, where you have f omega sitting here, and a second term where you have an f omega sitting here. Now, here of course you have an overall f factor for the whole sum. Here xi is going to act on f times a function. So what you get is f times xi acting on the function plus an additional piece. So if you take the f times xi acting on the function plus this, you do get f times d omega x1 through xk plus 1, of course with a 1 by c from the definition itself. But you also get this additional piece. And this additional piece, as we have already argued before, I don't really want to repeat that argument now, is nothing but the wedge product of df with omega given all of these arguments up to a factor of k plus 1. So what you need for our formula to be exactly Leibniz is for this 1 by c to be equal to k plus 1 so that we can cancel this from both sides and you end up with d of f omega is f times d omega or f wedge d omega plus df wedge omega. So this Leibniz-like property will be ours if we choose the constant c to be 1 over k plus 1. So our job is done. We have now a formula for an exterior derivative which is R linear, C infinity multilinear, alternating, and also obeys the Leibniz property at least when you have a function multiplying a form. And this is the definition. Of course, the definition itself should be pretty familiar to all of you who have been listening to these lectures, because this is the definition which we started our discussion on the exterior derivative with. But what we have achieved today is figure out for ourselves why the definition has to be precisely like this and nothing else. From the next lecture, we will return back to standard properties and problems in differential geometry. This, as I have already said, was more of a detour into trying to discover for ourselves the reason behind this rather complicated looking definition. Bye for today.